Online passive aggressive algorithms. It's not just how I use X. Welcome to this video on classification. My name is Kevin Fiesel, and I am the proprietor of Catalaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. Our topic for today is a class of algorithms called online passive-aggressive algorithms. This is a rather interesting approach, starting with a paper from 2006 that described the general idea. These algorithms follow three critical properties. The first property is that these are online algorithms. What I mean by this is that training happens one record at a time. We're used to scoring one record at a time, but training on batches of data. This is a rather different experience. We have our training process and it takes a single data point. One benefit to online training is that we only need a limited amount of memory, so our memory requirements will not grow with the dataset size. This is in contrast to many other algorithms, such as random forest, with the upshot being that you can perform model training on less expensive hardware than what you would need for most of the other algorithms that we have seen in this series, much less deep learning approaches. In this picture, I have the one data point I am training against as a hollow dot, and my classification space with some data points that I've already trained, showing either green dots or blue dots based on the class. I also have a blue line representing the gradient curve between the green class and the blue class. In this image, based on where our hollow dot appears compared to the gradient line, we will assume that this dot is blue. This leads me to the second property. The algorithm is passive. If we got the answer right, we make zero changes to the model. We simply move on to the next item in the queue and see how it does. But what happens if we got it wrong? In this case, we are aggressive. We shift the gradient until our latest data point becomes correct. If our data point was actually in the green class and not in the blue class, we're going to shift this curve until we can say that the dot obviously should be in the green class. What's important here is we don't care about any of the other historical data points. We can also shift the curve along any relevant axis. So if our next data point is a blue one, we want to move the curve. We can shift or rotate the curve with an emphasis on getting the current data point right. In this example, I purposefully rotate in such a way that we make the prior green dot a little more ambiguous. The reason I'm doing this is to show a reminder. Once we place that green dot and lay out the margin, we stop caring about that dot altogether. Let's go one step further and introduce a new blue dot, but one that we would initially figure to be in the green class. That causes us to shift the curve, so we'll do it just far enough to guarantee that we will estimate the data point in the blue class. And now look at what it does with our prior green dot. We would get that one wrong. But again, the algorithm doesn't care. This is an online algorithm, so we really don't look at what came before, just what we have in our current data point. You might be listening to this and thinking that the algorithm has to be terrible compared to others, but let's go to the demo and see how it actually plays out. This notebook will cover online passive-aggressive algorithms. This series of classifiers is the first example we have of an online algorithm. Prior to this, we have performed bulk training on an entire training dataset. Now, the algorithm we're using pushes data points one at a time in the order in which we present them. The passive-aggressive classifier class is in sklearn.linear model, so we're going to import it. The constructor for our passive-aggressive classifier looks a bit different from the other algorithms we've looked at, and it has several parameters. The first parameter is the loss function, and there were two of them in the original passive-aggressive algorithms paper. The default is called hinge, and the alternative algorithm is squared hinge. I am using squared hinge in this example, though because this is a fairly simple scenario, the choice of loss function doesn't really affect results very much. The next parameter is C, which is the regularization parameter. This defaults to 1.0, and I will leave it at the default. The maximum number of iterations is 1000, which again is the default. I'm setting a fixed random state to guarantee reproducibility. And finally, I'll set the tolerance parameter to 1e to the negative 4. The tolerance parameter tells us when we can stop. We'll stop when the difference between the current loss result and the prior loss result is less than this tolerance, indicating that we've stabilized our results. Our dataset is the same campus recruitment dataset that we've used a few times already, and I'm going to perform the same processing work that I did for logistic regression, k-nearest neighbors, and XGBoost. I'll drop the SL number, I'll drop the status, and I'll drop the salary parameters from X. Meanwhile, our label is the status column, so I'll make that Y. If we want to take a quick peek at the data frame, we have 215 rows and 15 columns. Subtract the 3 features we removed from X, and we will have 215 rows and 12 columns for our input data frame. I have some categorical features, so I will need to convert them to numeric features. To do that, I will use one-hot encoding. This one-hot encoding code is exactly the same as what we used for logistic regression, among others, so I won't spend any time focusing on it. This will give us a result of 215 rows and 21 columns for X. I can take a quick peek at X and make sure that things look the way I expect them to, and they do, so let's continue on. I'll use label encoding for Y, setting the value to 1 if we placed this student post-graduation, and 0 if we did not place this student post-graduation. Then I'll split the data into training and test subsets using the same test size and random state parameters that I used for other algorithms, so that way we get a more fair comparison. We'll check the XTrain data frame to make sure that we have 150 rows and 21 columns, and we do. Now let's perform training. To do so, I'll use the fit function, just like we have before. Even though this is an online algorithm, we don't have to change the way we write our code. That's all just happening behind the scenes. Now let's see how we did. If I generate a set of predictions and call the accuracy score function, I get a result of 84.6% for accuracy, which is good. That's right in line with our other algorithms. Now let's drill into the confusion matrix and classification report. Comparing our online passive-aggressive classifier to other algorithms we've worked with along the way, this algorithm is actually the best of the bunch when it comes to making placements. We got 41 of 44 right, which is better than any of the other algorithms. When it comes to non-placements, though, it's down near the bottom, beating only k-nearest neighbors. Granted, the test set size is small, but to the extent that there is interesting information in here, it is that we have a distinct trade-off between sensitivity and specificity. The more sensitive results are less specific, and we don't have a single algorithm in the bunch that does markedly better on both sides of this equation. Before I exit this demo, however, I should point out that online passive-aggressive classifiers are dependent upon the ordering of the input data. They can perform significantly worse on ordered datasets than they would on randomized datasets, so we should make an effort to shuffle our data before training, and that's what we did in our demo above. I hope you enjoyed this quick overview of online passive-aggressive algorithms. They are more of a niche group of classifiers, but within that niche, they tend to perform quite well. This is also going to wrap up my coverage of two-class classification. In the next video, we will pivot to multi-class classification. We'll have links and show notes in the description below, and until we see each other in the next video, take care.